So if you recall from last Friday, what we started with was exceptions to the Ionic rule, Ionic compounds. And we mentioned that ionics are formed whenever a metal, which wants to lose electrons and become positively charged, donates those electrons to a nonmetal, which wants to become negatively charged to fill out its valence. So metals are losing to go to 8 to fulfill the octet rule, or 2, but in most cases 8 to fulfill the octet rule. Nonmetals are gaining electrons to fill the octet rule. And so then when both of them have filled the octet rule by giving electrons, the metals give electrons, the nonmetals receive the electrons, they fulfill their shells, but then when they do that, a consequence of that is that they become charged, one positively charged, one negatively charged. The metals, which are neutral, give away negative electrons. They don't give away any protons, so they become positively charged. The nonmetals receive electrons. They don't gain any protons, but they do receive electrons, so they become negatively charged. And as a consequence of that, the positives and negatives attract each other, and they come together. And they come together in a way that neutralizes the charge of the overall molecule. Which is why if one atom wants to become a +2 ion, and you have and you have a nonmetal that wants to become a -1 ion, you need 2 of them to balance out the +2. Okay, so that's what we covered last time. We also covered ionization energies, electronegativity, and atomic radius. And remember the basic trends on those. Again, I'm just going to draw a rectangle that's supposed to represent the periodic table. But for ionization energy and electronegativity, the trend is up to the right is positive. So moving from left to right and from bottom to top is a higher ionization energy. It's also a higher electronegativity. Remember that ionization energy is the energy that think of it as the donating atom. How hard do they hold on to their electrons? We said that metals want to get rid of electrons, so they don't hold on very strongly. On the other side, nonmetals want to build, so they're not going to give up anything that they already have, which is why this trend is they have a higher ionization energy than this side. Also, electronegativity is the force that atom uses to steal electrons away. Again, metals aren't going to try to steal electrons away from anybody. They're trying to give up. Over here, those same elements which are holding on to what they have are also exerting a lot of force to get what they want. So the trend is, in a column, the higher it is on the column, the higher the ionization energy, and also the higher the electronegativity. The farther to the right, also in the same row, the higher ionization energy and the higher electronegativity. The other thing we talked about was atomic radius. We said atomic radius is a little bit counterintuitive in that it actually goes this way as increasing. What does that mean? As we go from top to bottom in a column, it should make sense that the atomic radiuses are increasing because we're adding energy levels. But at the same time, as we move from left to right, even though we're adding electrons to the atom as we build it using the electron configuration, even though we're adding electrons as we move from left to right, we're also adding protons as we build from left to right. And the electrons are not going into new orbitals, they're going into orbitals that have already been established. So you're adding electrons, but you're not increasing energy levels. But because you're adding a proton to the nucleus as you do the build, you're concentrating the positive forces in the center, it's actually pulling the electrons in tighter. So as you move from left to right, the radiuses get smaller. And as you move from right to left, the radii get bigger. And then from top to bottom, the radii get bigger. So you need to remember these 2 basic trends. Ionization, energy, and electronegativity. Up and to the right is positive. Radius to the left and down is positive. Okay, by positive I mean increasing. Okay? So that's a rapid review of what we did last time in terms of those 2 things. We also did Lewis dot structures for ionic compounds. Remember, the ionic compound is literally an exchange. You're trading or you're giving away an electron. And so we constructed the Lewis dot by putting dots that represent the valence electrons of each atom. And then we saw that the metal donates an electron to fulfill the valence of the nonmetal, but then again, because of the attraction between them, they come together. Today we're going to go to the next level, which is the covalent compounds. Those compounds which don't give or take electrons, they are nice communal sharers of electrons. They don't give or take, they share, okay? So that's the fundamental difference. If somebody asks you, what is the fundamental difference between ionic bonding and covalent bonding? You're going to hear the phrase, a physical bond. And again, physical bond, nothing ever actually touches anything, right? So what does a physical bond mean? We say physical bond in chemistry, we're talking about sharing something. There is more than just a casual attraction that's taking place here. There's a sharing commitment that takes place. And they're represented by a different kind of symbology when we put it on the board. So ionic compounds are formed by donating or receiving electrons and then attracting because of charges. Covalent compounds form because two atoms share an electron. And because there's something shared between them, they stick together. You know, think about it like in relationships, okay? These two, there's a child in the mix here, let's say, okay? These two atoms are not going to leave, because to leave means they lose their connection to this shared thing, this thing they have in common together. But in this case, it's a bond. More accurately, it's an electron that they're sharing. Now, they start this discussion about bonding and shared electrons by going over the homonuclear diatomics. And I've mentioned that several different times. So it's important, and they mentioned over here on page 151 that you're going to have to memorize these elements. These are elements that form in their natural state, in their elemental form. They are not individual atoms, they are molecules. Let's go ahead and just identify what they are. First of all, you have hydrogen. Symbol for hydrogen is H. Now we're going to jump over here to oxygen, or excuse me, to nitrogen. Nitrogen, oxygen, and then the column 7 elements. So you've got hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, iodine, and astatine. Okay? Hydrogen, and then you form the 7. Nitrogen, oxygen, fluorine, chlorine, bromine, iodine, astatine. Mm-hmm.
I was in a different table, and the columns were different. It was everything was switched up. I didn't know what it was. Is that
There's many different forms of the periodic table. This is one of the most standard kind. But yeah, there are different kinds. So for right now, we're back to this idea of the homonuclear diatomics. If I wrote on the board any one of these symbols, you should be able to tell me what that element is. Okay? What we're talking about now is naturally occurring whenever you were to say walking through a room and you were suddenly in a cloud of hydrogen. If you were able to go to the molecular level or the atomic level, we'd find out that hydrogen doesn't exist naturally in its elemental form as individual hydrogen atoms. It exists as hydrogen molecules. And it's true with every other one of these. Nitrogen exists as a nitrogen molecule. Oxygen, fluorine, chlorine, bromine, iodine, and astatine. In other words, if I were to come across an elemental, just a sample of pure hydrogen, I would have 2 hydrogen atoms bonded together, forming a hydrogen molecule. And the same thing would be true for every one of these. Just put in the different symbol here, and it represents the same thing. 2 atoms of that same element bonded together to form a single molecule of that element. So in the future, if someone were to say, you have 3 liters of hydrogen gas, you would not put H representing that gas, you'd put H2, hydrogen gas. Why? If you have a sample of material, you're going to have more than one atom of that material, right? And for these particular elements, they always bond with like atoms. We're going to explain why that is in just a moment. So again, you just need to remember that hydrogen, nitrogen, oxygen, And then the column 7 elements are the homonuclear diatomics. And they exist naturally in their elemental form as molecules, not as individual atoms. Okay. Now they use fluorine as the example in the book. Let me go ahead and use that as well. When we talk about covalent bonds, what type of atoms are we talking about? Metals or nonmetals? Nonmetals, right. Covalent bonds are when two nonmetals form a molecule, two nonmetals. Now the characteristics of a metal is it wants to give up electrons. A characteristic of a nonmetal is it wants to receive electrons, right? Not very willing to give up any, always wanting to receive. So we're going to use fluorine as an example here. If I were to draw the Lewis dot structure for fluorine, let's just say I have one atom of fluorine. How many dots would I put around this symbol? It's a column 7 element, right, Ray? It's a column 7 element. We're going to expect to find 7 valence electrons, the 2 that are in the s orbital and 5 in the p orbital. Okay? Now, just because I said before you're going to learn when the most appropriate way to draw these things, if I were to do it the way we've been doing it thus far, I would know that there would be 1, 2, 3, 4, 5, 6, 7, and just count around the symbol to place 7 valence electrons. If I were to tell you that there were other fluorine atoms in the area with this fluorine atom, right? Seldom do you find one atom of anything. There's usually clusters of them. As a matter of fact, we're going to talk about huge numbers of atoms of any given element at a time. 6 times 10 to the 23rd numbers, counts of these elements. But let's suppose there was another fluorine atom in the area. Another fluorine. It would have the same electron dot structure as the first. They're identical. This fluorine is looking to complete its octet rule, to fill out its valence shell. So it's looking to find how many electrons. How many does this fluorine want? It just wants 1. This fluorine is neighbor next door. It's looking for 1 as well. Okay? They both have high ionization energies. In other words, it's going to take a lot for them to give up anything. But they also have very high electronegativities. They both want and are willing to exert a lot of force to get an electron. But they're equally matched. A tug of war, it's a dead heat. They're perfectly matched. So what's going to happen is, in the ionic form, which does not happen here, I'm going to show you what does not happen first. What does not happen is, this one doesn't say, I give, you can have it, boom, there you go. Because what's just happened over here? It's farther behind in the octet rule, right? In a metal, it gave up and it completed its octet rule when it gave up electrons. Now, this fluorine situation is even worse. And this one is satisfied, it's done, it's not looking for any more reactions. But what actually happens is you have this situation, and just for ease of diagramming, I'm going to change the structure slightly, because you're going to find that you can do this. There's my original 7, and here's my original 7. What these two atoms decide they're going to do is, since neither one is willing to give up and both are fighting hard to get, they're going to share. And we show a shared electron with a solid bar. They decide we're going to share an electron. Actually, we're going to share 2 electrons. At times, this atom is going to be over at its neighbor. At other times, the electron that was formerly here is going to be over here at this atom. A shared electron, in terms of the octet rule, is considered to be part of the valence of both atoms. Both ions now, right? The shared electron is considered to belong to both. So as we do the octet, as we count up, how many valence electrons does this fluorine atom see? 1, 2, 3, 4, 5, 6, 7, 8. This bar, which represents the shared electrons, is counted as 2. 2, 4, 6, 8. And this side, 2, 4, 6, 8. Now they're done seeking electrons. Now their valence shell is full. Both fluorines are satisfied. There's a relationship here. They bond together. This is what was referred to in chemistry as a physical bond. Okay? Again, we'll argue with the technicality if it's physical or not, but this is what it's called, a physical bond. They're bonded together because they're sharing an electron. And for you to break them apart takes a lot of energy. For an ionic reaction, all you got to do is mix it in water, right? Here, you've got to break a sharing relationship, and it takes a lot more energy. So the fluorine has its octet full. This fluorine has its octet full through the sharing of these two electrons. And this is the exact same diagram that's going to take place for every one of the column 7 elements. If I were to put chlorine in here, if I were to put bromine, iodine, astatine, put them in either one of these two, the molecular Lewis dot structure will look exactly the same, because every one of those column 7 elements has 7 original, and because they're in proximity to another of identical their own kind, they will automatically begin sharing an electron and form homonuclear diatomic molecules. Okay? So the homonuclear diatomics represent one of the easiest ways, the most symmetrical ways we'll learn later, because both of these nuclei are exerting the same positive forces on those electrons, that they are both pulling with the same exact force, and so the electrons are going to be perfectly equally shared. This one is pulling the same as this one, so in the sharing relationship, they both get an equal share of the electron. Think of it as you and your friend, you both want to have a car, but neither one of you can afford a car. But together you can afford a car. You decide to have a car, and you work out a relationship where sometimes it's parked at your house and sometimes it's parked at their house. Your house, their house. Your house, their house. Your house, their house. That's what's happening here. They come together and say, we both need one electron. Sometimes we'll share. Sometimes you give me yours, and sometimes I'll give you mine. Back and forth, back and forth, back and forth. It happens incredibly quickly, but they're sharing this electron back and forth between the two of them. So both of them have the sense that their octet is full. Yes?
Do the electrons move in the same way that we think they do between orbitals?
If you think of it as, like in here, making a figure 8, conceptually you can understand it that way, but it's not that clean. Don't get into where does it actually exist at. For right now, just think of this as a Bohr model rather than a... We'll reduce it down to the Bohr model because it gets too abstract. Okay. But if you were to think of it like a Bohr model, you might think of the shared electron as sometimes it's over here, and sometimes it's over here. Sometimes it's over here, and over here, and over here, and over here. And you have an electron that's being shared back and forth. Conceptually, that's one way you could understand it. And when the electron's over here, they have 8. And there's a greater pull maybe from this side, so as it orbits around, it gets pulled back into orbit over here. But because they're both the exact same forces, it gets shared perfectly equally. Maybe you can see that as one rotation and one rotation, and one rotation, another rotation, one rotation, and another rotation. Okay. So this idea of drawing the valence, the Lewis dot structure for a nonmetal, and then organizing the pieces so that we share electrons to complete the octet rule is the principle we're going to use moving forward in here. Let me make sure I've covered everything in the book. Let's see, 151, homonuclear diatomics. Remember that the homonuclear diatomics, they form this kind of molecule only in their elemental form. That doesn't mean after they've reacted that they can't be just one hydrogen, for example. Hydrogen forms H2 molecules, but when you form water, it's H2O. It's not H2O because it's a homonuclear diatomic. Remember, oxygen's a homonuclear diatomic too. So H2O, to form H2O, the bond between the two oxygens has been broken so that you can use one atom of oxygen. So that, again, because it's homonuclear diatomic doesn't mean it only can be in molecules in segments of 2, 4, 6, 8, and so on. When you have a reaction that forms a new molecule, such as water, you do have the two hydrogens, but they're going to bond to the oxygen as well. So an elemental molecule of oxygen had to be broken into two, and half of that used to form one molecule of water to form H2O. So the homonuclear diatomics can separate to form other molecules, but when they are coexisting in the same place at the same time with others just like themselves, they don't just sit there as individual atoms. They automatically form bonds and create molecules of themselves. For hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, iodine, and astatine. It's unique because of bonding. We'll get into more advanced bonding probably tomorrow. So remember, in covalent bonds, the electrons are not transferred like they are in ionics. In ionics, ownership of the electron is changed from the metal to the nonmetal. Okay? Ownership goes to the nonmetal of that electron. In covalent bonding, it's shared. It never completely loses attachment to its original, but it's occasionally shared with its neighbor molecule or neighboring atom. On page 152 in the blue, covalent bond, a shared pair of valence electrons that holds atoms together in covalent compounds. This shared electron is considered to be a covalent bond. And just below that, the same encouragement I just told you. The atoms in covalent compounds share electrons. The ionic compounds give and take electrons. They have us next consider the compound carbon tetrachloride. Let's think about that for a minute. Carbon tetrachloride. We've got carbon. Hopefully now you know we've got chlorine. Carbon is a nonmetal. Chlorine is a nonmetal. So we got two nonmetals. Okay, now we're going to talk about covalent bond. If I said, what's potassium chloride? You go, that's a metal and nonmetal, it's ionic. They're going to give and take electrons. Here it's a nonmetal, nonmetal. Okay, now we're talking about sharing electrons. What do the Lewis dot structures look like for both of these elements? I'm just going to draw one chlorine for now. Carbon, how many valence? Column 4 element has 4. So 1, 2, 3, 4. Chlorine, you see this column 7 element, right? Now one of the things you're going to learn very quickly is if, okay, I'm going to be bonding these things together in some way, I'm going to put my lone electron, my single electron, towards another element. So I know here I'm going to have 7 dots. I'm going to go ahead and place the single dot near the neighbor and complete the shell with the others. So I see chlorine has 7. I put the single close to the carbon. It's carbon tetrachloride, right? Carbon tetrachloride, 4 chlorides. Well, as I said before, carbon is one of those major master links we have in our chemistry, the chemistry that we're familiar with, carbon-based chemistry. I can go through then and put 4 chlorines . 7 dots around every chlorine, and I orient the lone electron towards another element. In just a moment, I'll tell you how I knew to do it like this. How many valence electrons does this chlorine currently see? 1, 2, 3, 4, 5, 6, 7. How many does it want to see? 8. Needs to share 1 from its neighbor to get 8. There. Now the chlorine sees 8. Because this is a symmetrical molecule, it's a tetrahedral. We're going to find out those geometries in probably another module or so. That this same kind of a bond happens for every one of them symmetrically. So it shares these two are shared, and these two are shared. All I'm doing is replacing a pair of electrons with a bar to show that it's actually 2 electrons being shared back and forth. Now, go to the perspective of each one of these atoms and say, how many valence electrons does it see? This chlorine, 1, 2, 3, 4, 5, 6, 7, 8. This one, 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. How many valence electrons does the carbon see? 1, 2, 3, 4, 5, 6, 7, 8. Every atom sees 8 valence electrons. Every atom has completed its octet rule, and that we now have a stable molecule of carbon tetrachloride. If you flipped over to 154, they give you a 5-step process when you're building up a molecule using this method of how to kind of get to the geometry quicker. See the first one, go through the different steps. They suggest the following steps. First, count the valence electrons in the entire molecule by adding up the valence electrons of all the individual atoms. So originally it was 7, 14, 21, 28 plus 4 for carbon is 32. 32 valence electrons. It says put the atom with the most unpaired electrons in the center. See, I've done this enough times that I looked at carbons and chlorines and I said, okay, wait a minute. Chlorine has 7. It only has 1 unpaired electron. Carbon has 4. It has 4 unpaired electrons. So whatever my structure is going to look like, my atom with the most unpaired electrons is going to be in the center. Okay? Because it needs the most connecting points. You guys had those little toys that you build structures with and things like that. This is like the hub that has all those holes around the outside, right? I'm going to form up a molecule. I'm going to bring these pieces together. I want the one that has the most ability to connect with other things in the middle, and those that maybe can only connect to one other thing on the outside. So as I looked at this, carbon and chlorine, carbon had the most available electrons to be paired. Another way to say that, the highest number of unbonded electrons, or non-paired electrons. It had 4 of them. And that's the case with every column 4. Carbon, silicon, germanium, tin, lead, they have 4 valence electrons, which means they can potentially connect with 4 other things and form a tetrahedral. Okay? So since between chlorine, which has 1 unpaired electron, and carbon, which has 4 unpaired electrons, carbon gets to be the center of my molecule when I build it. That's step 2 in the process. Number 3, arrange the other atoms around the central atom and bond them with a single covalent bond. So I orient them around, I draw the Lewis dot structure, and I put the unpaired electron closest to the unpaired electron for my centerpiece, and then I form single bonds. Now this doesn't mean that after you form single bonds, everything's going to be satisfied, but it's the next step. It's the next step in forming that bond. Then it says fill in the octets of the outside atoms. And as we do more advanced structures, that'll make more sense. And then make sure that the central atom has its octet. We made sure the central atom had its octet, but we also counted around and made sure that every of the peripheral atoms had their octet as well. In this case, every atom up here has satisfied its octet. So example 4.5 gives a couple, actually this one is just H2O, building water. Let's go through and build a molecule of H2O using these rules that we just learned. H2O. What are the elements that are involved in this? Individual atoms now. We've learned that hydrogen is a homonuclear diatomic, so we know in order to have an H, we've had to break down an H2 molecule because it's naturally a homonuclear diatomic. But the elements that make up H2O are simply hydrogen and oxygen. Okay. What does the valence for the hydrogen look like? How many electrons does it have? Just 1. And I know I'm going to be bonding here, so I'm going to go ahead and orient it towards oxygen in some way. So I'm going to put my 1 right here. Oxygen, how many valence? Okay, 6. So I know I'm going to have 2 pairs and 2 singles, right? I know I want to put at least 1 towards there. There's my 6. 1, 2, 3, 4, 5, 6. Now I could have, if you're not comfortable intuitively rotating your available electrons, I could have just done it 1, 2, 3, 4, 5, 6. But then I would drive my hydrogen near one of the unpaired electrons. For ease of looking left or right, I'm going to do it this way for right now. So between hydrogen having 1 unpaired and oxygen has 2 unpaired, my oxygen is going to be my hub. Then arrange the other atoms around the central atoms. I have another hydrogen, right? For H2, I need to have another hydrogen. And I'll put my other one towards. Now I've already slanted this because I know something you guys may not know. So I'm going to go ahead and fix it just to be kind of as neutral as possible. I'll put my other hydrogen down here. Okay. Now I'm going to go through and put in my bonds. I'm going to take those unpaired electrons and I'm going to pair them. I'll make that a pair, make that a bond, and make that a bond. Now I'm going to go through and see if I have my octets. My octet rule has been satisfied. Okay? For this hydrogen, how many electrons does this hydrogen see? 2. How many does it want? 2. It sees 2, it wants 2. This hydrogen is done. What about this one? Same thing, right? It wants 2, it sees 2, it's done. What about the oxygen? 1, 2, 3, 4. This bond is 5, 6. This bond is 7, 8. Oxygen sees 8. So hydrogen sees 2. The other hydrogen sees 2. The oxygen sees 8. The octet rule is satisfied. This is the Lewis structure for H2O. And one of the things you're going to learn later on is that this is a 2-dimensional drawing of a 3-dimensional object. And you know, that just like we talked about, it's hard to visualize the orbitals because, you know, we can say the S is a sphere, but I'm actually just drawing a circle. And I have to try to represent that in some way to let you know that it's actually a 3-dimensional circle, it's a sphere. In the same way, this is H2O, but this is laid out flat on the board. There is some dimensionality to it, but this is a flat molecule. What's going to change a little bit, though, is how the angles between them vary based upon the structure, and that'll be, again, another module. That's why, just to give you a hint, when I put this on the board the first time, I kind of drew it like this. That's actually starting to present it more like a 3-dimensional picture. So for where we're at right now, we're just going to do it vertically like that to form my H2O. Rather than moving on to the more complicated Lewis, let's go ahead and try the on your own 412. Why don't you go ahead and start ahead of me. I'll give you a little bit of time, give you a head start. So we're forming the molecules NH3, SiBr4, H2S, and ICl. Just give it your best shot. So the first one is NH3. Give you a few minutes to do that molecule, then I'll do it. And then we'll go on to try the next one. In fact, I'll work it on the board. You can work it on your paper, and then we'll look up in a moment. So. My nitrogen it's a column 5 element. And again, by experience, I'm going to do this. If you did it another way, that's fine. But I'm going to have 2 dots together and then 3 dots around the different sides for a total of 5. How many unbonded electrons do I have? 3. Hydrogen. We already done hydrogen, right? And again, because I'm starting this, I'm going to draw my unbonded pair, or my unbonded electron towards, but it only has 1. So nitrogen is going to be my center. And the great thing about this is symmetry in nature. If I have 1 of one thing and 3 of another and they're bonded, what's probably going to be the hub? The thing I have 1 of, right? The 1 is going to be the center, and symmetrically the other 3 are going to form around it. But in this case, nitrogen has 3 unbonded, hydrogen has 1 unbonded. I have 3 hydrogens, and so I'm going to put those around towards the unbonded electrons and put their unbonded electrons on the diagram as well. Now I'm going to go through and connect every one of them with a single bond by connecting these electrons to show that they're shared. Shared, shared. So two-dimensionally, this is what the Lewis structure for NH3 looks like. This is ammonia. Ammonia, NH3. It's got an unbonded, it's got a pair and 3 unbonded electrons that are being shared with 3 hydrogens. Nitrogen, does it have its octet satisfied? In this form, in this molecule, is nitrogen's octet satisfied? Just count them up. Count them up. Here's 1, 2, 3, 4, 5, 6, 7, 8. Nitrogen's octet is full. Hydrogen's octet rule, it's looking for 2. It's one of the exceptions. 2, yes. 2, yes. 2, yes. They're completely satisfied. This is your stable NH3 molecule. SiBr4. Just on the basis of symmetry, what is going to be my center? Silicon, right. Silicon is going to be my center. I would also know that because silicon is a column 4 element, which means it's got an unbonded electron at every 4 coordinal positions. Bromine is column 7, which means it has 1 unbonded electron and 3 pairs. Because silicon has the highest number, back to the rule, highest number of unbonded pairs, or unbonded electrons, it goes in the center. I've got 4 bromines I need to place. I'm going to do the same thing. I'm going to orient the unbonded electron towards my silicon. Now I'm going to go through and connect or bond each one of them using a single bond to start with. And I should recognize now that every one of the bromines has its octet completed, and the silicon has its octet completed completely through sharing. 2, 4, 6, 8. 1, 2, 3, 4, 5, 6, 7, 8. So that's the Lewis dot structure for silicon tetrabromide. Silicon tetrabromide. Okay. What was the third one? H2S. Sulfur has column 6, just like oxygen. Okay. Hydrogen is 1. Get another hydrogen here. 1. Connect them. 2, 2, 1, 2, 3, 4, 5, 6, 7, 8. We're done. Notice this is exactly the same as H2O, right? Because oxygen and sulfur, same column, both column 6. So sulfur here. There's my H2O. Oh, guess what? Oxygen, what's after oxygen? Silicon, cesium. I bet you look just like that too. Or the next one down. Because remember, chemically, the number of valence electrons is what dictates the chemical behavior of the element. Every one of those in that column have the same number of valence electrons. So the diagram is going to look exactly the same in 2 dimensions. But in our case here, it was S. Okay. What's the last one? ICL. Iodide and chlorine. Cl. These are both column 7s, right? I'm going to put the unbonded to the middle. Put my pairs around the outside. There we go. Just remember that the bar symbology represents 2 electrons being shared. Okay, you may not, it's not technically 2 dots connected with the bar. The bar replaces those 2 dots. So, but for practice, as you're learning this, leave your single unbonded electron towards a single unbonded electron, and then connect the dots. That represents that bar, those 2 being shared. Okay, now there's more complicated ones. Not only, these are all like column 7, right? When the homonuclear diatomics, whether it's 2 fluorines, 2 chlorines, 2 bromines, 2 iodines, 2 acetane, or 1 and 1, 1 and 1, since they're all column 7 elements, they all have 7 valence electrons, they're all going to combine with each other in this way. But what do we do with oxygen? Oxygen, we said, is a homonuclear diatomic as well, which means that if we have 2 oxygen atoms next to each other, they're going to form a molecule, an O2 molecule. Let's try to chart that one out. We've got oxygen here and oxygen here. How many valence electrons does oxygen have again? 6, right? Let's draw the 6. Do you agree that that's 6 around both? Okay. Now it says whichever one has the most is the center, but for symmetry here we've got 2 identical, so there is no center. There's just left and right. We're going to start by making a bond. We're going to connect these 2 by replacing the symbology of these 2 electrons and say, okay, those 2 are shared. Is the octet satisfied for those 2 atoms now? Had 1 response, but can you see? Is it or isn't it? Count them up. How many are around each oxygen? How many does each oxygen see? That's another way to put that. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. The octet's not satisfied, is it? They both want 1 more. So we'll do that. We'll move this one over here, and we'll move this one over here, and we'll bond them again. Now how many does each oxygen see? 8. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. You've just been introduced to a double bond. Okay? And technically what's going to happen, you'll see in 2 dimensions, is that these are going to repel each other and they're actually going to start forming up over here so that they're equidistant from each other. For right now, this is technically better, but the way you were doing with 2 and 2, that's fine for now. The most important thing is to see that there's a double bond taking place. And by sharing these electrons, both of them are satisfied. And this is what an O2 molecule looks like. An elemental oxygen, O2 molecule, are 2 oxygens with a double bond between them that holds them together. But we're not done. Nitrogen. I've got 2 nitrogens. They have how many valence electrons in their natural form? 5. Let me start with 1 each on the inside. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. If I bond these two, how many do each see? Now they each see 6. Now how many do they see? Now how many do they see? 8. It's a triple bond. So you've got a single bond, this is a double bond, this is a triple bond. And because of forces, this pair is actually going to move to the outside because it's going to be repelled by the others. Okay? What do you think has the most strength holding them together? A single bond? So you've got fluorine, or chlorine to chlorine. A single shared pair, 2 shared pair, or 3 shared pair. Think of it as chains, man. This is strong, but this is stronger, and this is even stronger. Okay? The number of shared pairs, the number of bonds that you have. And you can see this working the triple bond, page 157 to 158. And they show you, like I did, how the unbonded pair gets shifted to the outside to show that triple bond. Now there's some very practical applications for the triple bond, which we'll get through tomorrow, and that will complete the module.